Here we are in the lab at Profactor, at which the demonstrator of use case 3A is set up. At use case 3A, we use active thermography to inspect forged parts like this camshaft. The goal of the inspection is to detect cracks on the surface of the part. Behind me, we see the enclosed work cell that protects the user from the robot as well as from the laser that is used to heat up the part. The laser won't turn on if the door is open, and also the robot won't move at full speed at an open door. At use case 3A, the camera as well as the laser is fixed and the part is moved by a robot. The camera is provided by Infratech and provides frames at a rate of 151 images per second and has a resolution of 640 times 512 pixels. Within the SPIRIT project, Infratech tries to optimize their cooling technology and tries to minimize vibrations in order to optimize the image quality. This will also improve the accuracy of the image projection algorithms that are implemented in SPIRIT. The laser is a 100 watt CO2 laser with a wavelength of 10.2 micrometers, so it is not visible to the human eye. The FANUC robot can carry up to 50 kilograms, so it is possible to even inspect heavier parts than the used camshaft. During the inspection, each spot on the surface must first be heated up by the laser. Afterwards, its cooling down behavior is captured by the camera. And in order to compute a suitable path for the inspection, it is therefore important to know the exact position of the laser beam as well as the exact camera position. The University of Padua developed during the SPIRIT project algorithms that can achieve a very high calibration of these components. Before the inspection of a test object can be performed, a robot path that covers the surface of the object is needed. This task is done by the work cell simulator of IT robotics. The goal of this offline path planning is to compute the fastest trajectory that fulfills the following three conditions. All visible areas of the surface of the object must be covered. No collisions should occur, and all Cartesian positions must be reachable by the robot. In the first step, the inspection task is configured. Here, a CAD model of the work cell needs to be loaded. The positions of the laser and the camera within this CAD model is determined by the hand-eye calibration. Parameters like the camera intrinsics are used to set up the generic process model. After the inspection setup is configured, the user can select the areas on the test part that needs to be inspected and starts the computation of the path. The inspection trajectory is shown after the computation is finished, and it can be exported as HDF5 file if the user is content with the result. The inspection process itself is controlled by the inline framework. At first, the HDF5 trajectory file of the work cell simulator is loaded. After the connection to the camera, laser and robot is established, the inspection is started. There are three views that allows the user to monitor the progress of the inspection. The work cell view shows a 3D model of the setup together with the current robot position. The second view belongs to the image analysis. This algorithm searches for defects on the part. It generates result image which contains the found cracks. Each result image is assigned to a robot position by means of its timestamp, and the resulting pair of image with position is sent to the image projection algorithm of the University of Padua. Here, the images are back projected onto a 3D model of the test part. Thereby also the coordinates of the cracks are recovered. Their positions can be used to set up the grinding process at which the cracks are removed.